Hello and welcome back to the course on machine learning. Today we're talking about the polynomial regression. So let's get straight into it. We already know a couple of types of regressions. We know the simple linear regression, which we can see over here. Then we've also discussed the multiple linear regression, which is written out over here. And finally, we've got the polynomial linear regression, which is written out here. So notice how it's very similar to the multiple linear regression, but at the same time, instead of the different variables like x2, x3, x4, and so on, xn, we have the same variable x1, but it is in different powers. So instead of x2, we have x1 squared. Instead of x3, we would have x1 cubed. And so instead of xn, we would have x1 to the power of n. So basically we're using one variable, but we're using the different powers of that variable. So let's have a look at when you'd use a polynomial regression, when it would come in handy. Let's say we've got a set of observations which look like this. Then the line that fits this data is obviously a simple linear regression. As you can see, it fits it quite well. But let's for a change say that the data set looked something like this. So if we try to use a simple linear regression here, which is expressed like that, you'll see that it doesn't fit quite well. So in the middle, you've got data underneath, and then as you go further, the data will be above the line. So how can we correct that? Well, we can try to correct that by using a polynomial regression. Let's have a look. So instead of the linear regression, we're going to conduct a polynomial regression, and that, in this case, fits perfectly. And what is the formula? Well, that is the formula for this particular case. Y equals b0, so that's the constant, plus b1 x1. So that's a simple linear regression part, but then we're adding the b2 x1 squared. And the b2 x1 squared gives it that parabolic effect, so that the curve becomes parabolic, and therefore it will fit this data better. As you can see, polynomial regression is a bit different to simple linear regression. And at the same time, it has its own use cases. So it's all comes on a case-by-case basis. You have a problem, and then you might try a simple linear regression, a multiple linear regression, if you have many variables, or you might try a polynomial linear regression and see what happens. And sometimes the polynomial regressions do work better. For example, they're used to describe how diseases spread, or pandemics and epidemics spread across territory or across population. Polynomial linear regressions can be handy there, and they also have other use cases. So it's a matter of what works best. So it's always good to have more tools in your arsenal. And we have one final question left. The question is, why is it called linear still, right? So we saw those different powers, squared, cubed to the power of n, and so on. Why is it still called linear? And I'll show you what I mean. If you look on the left here, it says polynomial linear regression. So why is it still called a linear regression if it's a polynomial regression? Well, the trick here is that when we're talking about linear and non-linear, we're not actually talking about the x variables, right? So even though they're non-linear here, the relationship between y and x is non-linear, when you're talking about the class of a regression, you're talking, so whether it's linear or non-linear, you're talking about the coefficients here. So that's the interesting part. So whether or not this function, which we have here, so y is a function of x, right? And so the question is, can this function be expressed as a linear combination of these coefficients because ultimately they are the unknowns, right? So your goal when you're building a regression is to find these coefficients, find out their actual values, so that then further down the track, you can use those coefficients to then plug in x and predict y, whether it's a linear, a simple linear, multiple linear regression, or polynomial linear regression. That's your goal, to find these b coefficients. And that's why linear and non-linear refers to the coefficients. So an example of a non-linear regression would be if the equation was y equals b0 plus b1 x1 divided by b2 plus x2, or something like that, or b0 divided by b1 plus x1. So a situation where you really cannot replace the coefficients with other coefficients to turn the equation into a linear one in regards to the coefficients, not the x values. So there you go. That's why polynomial regression is still called a linear regression. That's your fun fact for the day, and maybe you can show off to your colleagues. And also, because of that, the polynomial linear regression is actually a special case of the multiple linear regression. So that's just something to also kind of note, that this is a version of the multiple linear regression. rather than a standalone, absolutely new type of regression. So I hope you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy machine learning.
Hello my friends, welcome to this new practical activity on polynomial regression. This time we're going to learn how to build together a nonlinear regression model which will allow us to tackle a problem with a nonlinear dataset, meaning a dataset with nonlinear relationships on which therefore a multipolinear regression model would not be relevant. Alright, so as usual, I just want to make sure here that everyone is on the same page. So right before this tutorial, I gave you the link of this folder. So make sure to connect to that link and you'll be inside this page just like me, ready to start this new polynomial regression model. And now we're all going to go into part 2 regression. We're still learning on how to predict a continuous numerical value. And this time we're going to go to section 6, polynomial regression, to learn how to build indeed this nonlinear regression model. All right, and as usual, we're going to start with Python, inside which you will find two files, polynomialregression.ipynb, which is of course your Python implementation, which you can open either in Google Colab or Jupyter Notebook, and the dataset called position salaries. All right, so as usual, we're going to start by describing the dataset. Once again, I'd like to remind that this is a simple dataset, and that's only, because we're starting with our journey of machine learning. So right now, I want to work on simple datasets so that you can focus on how to build the models themselves without being too overwhelmed by a complex dataset. But no worries, the further we progress in this course, the more we will work with real-world and complex datasets. You will see at the end, we will work with datasets with many more observations and more complexities. All right, so no worries about this. We will get there little by little. So what is this dataset about? Well, let's imagine the following scenario. Let's imagine that we are actually an HR department and that we want to hire someone. And we actually found someone that seems to be a great fit for the job. So we would like to offer this person a position in our company. And so this person says yes, but at the end of the interview process comes the inevitable question, what is your salary expectation? And let's say that this person is, very well advanced in its career, and therefore that person is asking for $160,000 per year. And then also as HR negotiators, we ask this person, why are you expecting such a high salary? And this person replies, well, that's because that's what I earned in my previous company. That was my salary in my previous company. I earned $160,000 per year, so I'm expecting at least $160,000 per year in your company. Is that the truth or is that a bluff? Well, that's exactly what we're going to figure out thanks to our polynomial regression model. We're going to build a polynomial regression model to predict the previous salary of this candidate. So how are we going to do this? Well, of course, in order to make such a prediction, we need data. And that's exactly the data we collected here. So what is this data and how did we collect it? This data is actually the different salaries of the previous company for the different positions from business analyst to CEO. And now how did we collect such data? Well, there are many websites online which actually display the different salaries of the different positions in companies. I can give you an example like Glassdoor. Well, let's say that we did this, and that's how we collected all this data containing all the salaries for the different positions of this previous company for which this person worked. Okay? So we have this data. And now we need to know, obviously, which position this person had within this previous company. Well, that's easy. Let's say we went to LinkedIn and we checked out the profile of this person, and we actually saw that this person was actually a region manager. Okay? However, on the LinkedIn, we also see something else. It turns out that this person actually has been a region manager for quite a while, like let's say 2 years. And therefore, the salary of this person should not exactly be $150,000, as we can see on this dataset. But instead, it should be somewhere between $150,000, the salary of position number 6, and $200,000, the salary of position number 7. So in order to extrapolate, we're going to suppose that this person has a position in between 6 and 7, and we'll consider this position to be 6.5, so that then we can actually deploy our model, after training it, of course, on the position level 6.5, so that we can get the predicted salary of such a position level. And we will compare this predicted salary to the salary expected by this person to see if indeed there is truth or bluff. Alright, so that's the strategy. It's basically going to be in 4 steps. First step, data preprocessing. Second step, we will build the polynomial regression model. Third step, we will train it to understand the correlations between the position levels and the salaries. And fourth step, we will make that prediction. Now, time to brainstorm together on what are going to be the first steps, within that data preprocessing phase. Well, of course, we'll start by importing the libraries. Then we will import this data set. But then, do you think we actually need to split this data set into the training set and the test set? Well, here, exceptionally, because we have very few observations, we actually won't split the data set into a training set and a test set, because what we want to get directly is actually that prediction of the position level between 6 and 7. We will say 6.5. So we actually need to get the maximum data we can, and that's why we're going to take everything to train our polynomial regression model. So exceptionally, we won't apply that third sub-step of the data preprocessing phase. And then obviously we won't have to use any other tools of the data preprocessing toolkits like taking care of missing data or encoding categorical data, simply because here we will just train our polynomial regression model on these 2 columns, level and salary, because indeed this column is just redundant with this one, right? It's as if the encoding was done simply on a spreadsheet. So we will actually not include this column. We will train our polynomial regression model with this column as the column of features, the matrix of features, even if there is only one feature, and this column as the dependent variable vector. All right, are you ready? Let's do this. Let's build our polynomial regression model. So we're going to open our IPYNB file or Python file. You have the choice to open it with either Google Colaboratory or Jupyter Notebook. And for Google Colaboratory lovers, let's open this right now and let's see what we have in our notebook. Laying out notebook, and there we go. So I remind that this notebook is in read-only mode, and since we, as usual, want to re-implement this from scratch, we're going to go to File here to create a copy by saving a copy in Drive. And as you see, it is creating a copy in which we will be able to re-implement the whole model from scratch. And there we go. All right, so now, as usual, we're going to delete all the code cells so that we can re-implement this from scratch. Make sure to only delete the code cells and not the text cells so that we can see the structure. You're starting to know the story now. And lastly, this one. Perfect. All right, so this is the whole structure of this implementation. Let's have a look. I already brainstormed with you on what would be the first steps, but I really want you to clearly see the whole structure, okay? So we're going to start by importing the libraries, then importing the dataset. Then, as I told you, we're going to skip the step where we split the dataset into the training set and the test set, simply because we want to leverage the maximum data in order to make our future prediction of the salary for the position level between 6 and 7. So we skip this step, and then we move on directly to first actually the training of the linear regression model on the whole dataset. And that's for the simple reason that we want to compare the 2 models, linear regression and polynomial regression, because I want to show you that indeed a polynomial regression model will be much more adapted to this dataset. And you know the reason? That's because the dataset has nonlinear relationships. So in the end, we will actually, as you can see, predict the salary of the position level between 6 and 5 with linear regression and polynomial regression. And you will see that we will get a much better result with polynomial regression. Okay? So after training the linear regression model on the whole dataset, we will train the polynomial regression model on the whole dataset as well. Then we will visualize the linear regression results on the whole dataset again, and then the polynomial regression result. And once again, you will see that indeed the polynomial regression model is much more adapted to this nonlinear dataset than the linear regression model. And finally, we will make our last 2 predictions, predicting a new result with linear regression and predicting a new result with polynomial regression. And at the same time, you will learn how to make a single prediction, because what we've done so far, when making predictions, was to input the whole test set features. You know, we input X test in our predict method, and that returns indeed some predictions of the test set, but you actually still don't know exactly how to predict the result of a single observation. And that's exactly in this practical activity that you will learn it. Okay, so that will be a good new skill to know, and I will of course ask you to try to do it on your own before we do it together. And so there you go, that's the whole structure, and now we're ready to start, and we're gonna tackle this semi-data preprocessing phase in a flashlight, starting by importing the libraries, and thanks to our data preprocessing template. So I'm copying this here, pasting that right here in a new code cell, then we're gonna import the data set, using still our data preprocessing template, because indeed we will have only one thing to change, which is of course the name of our data set. No, actually, my mistake, we will have two things to change, and I will explain why right away. So first, let's change that obvious thing, which is the name of the data set. So let's see the name of the data set again, position salaries. All right, so let's do this. I'm going to replace data here by position salaries. Great. And now the second thing I wanted to change is of course the matrix of features X, because remember that this automatically takes all the columns except the last one, but actually here, you know, these two columns are redundant. It's like we already did the label encoding, you know, to encode each of these positions into numerical integers going from 1 to 10. But I wanted to leave that column because it's pretty nice to see the names of the different positions, you know, from business analyst to CEO. So we actually don't want to include this column, and therefore we will start to get the column from the second index, which is index 1, right? Because indexes in Python start from 0. So there you go. We're only going to take that column, and to do so, well, we're going to replace that empty lower bound, which means the first index, by index 1, so that it will indeed take all the columns from the second one, you know, of index 1, up to the last one except the last one, and therefore it will take all the columns from this one except this one, and therefore just this one. See, just a simple trick. All right, so now we're all good. This will still take the last column, the dependent variable vector containing all the salaries, so we're all good, and we can move on now to the next step, which will be to train the linear regression model on the whole data set. Great, so would you like to execute this now? Yes, maybe let's do it now so that it's done. So let's click this folder here to be able to upload the file. Right now it is connecting to a runtime to enable file browsing, and in a second, yeah, there we go, we should be able to upload the dataset. All right, so we're gonna go to our machine learning A to Z folder. I always put it on my desktop, then part 2 regression, then section 6 polynomial regression, then Python, and there you go. Let's get and upload our position salaries dataset. That's all good. Now we have it, so now we can run these first two cells. First importing the libraries. Okay, done. And now importing the dataset. And done as well. And now we can move on to the next step, training the linear regression model on the whole dataset. So try to do it on your own, because you now know how to implement the linear regression model. So I trust you will smash this. There is no trap, and this will be a good way to practice again. So as soon as you're ready, well, let's move on together to the next tutorial to build that first linear regression model together, and then the polynomial regression model. And until then, enjoy machine learning. Hello, my friends. All right, so let's implement quickly and efficiently the linear regression model on the whole dataset. First, a quick reminder on what is the linear regression model that we're about to build. We're simply about to build this one, right? Because we have only one feature, which is the position levels, and the dependent variable, which is of course the salary to predict. All right? So that's what we'll do first, and then we'll of course implement the polynomial regression model with, I will tell you how many powers of that same position level feature. Okay, so let's do this, starting by creating a new code cell. All right, so I hope you did it yourself first to make sure you refresh your skills. And so if that's the case, of course you started from the scikit-learn library, because that's the library that contains this linear regression class, which allows to build the linear regression model. So scikit-learn, from which we're going to get access to the linear model, which contains this class. And from this linear model, we're going to import the linear regression class, as Google Colab guesses perfectly. Perfect. So that's the first step. Then we're going to create an object of this class. So I know we used to call it regressor, but this time, since we're going to have two regressors, we're going to have the linear regression regressor and the polynomial regression regressor. Therefore, this time I'm going to call it linreg for linear regressor. Okay, so linreg will be created as an object of this linear regression class. So I'm copying and pasting that here, adding some parentheses. And remember, we don't have to input anything in these parentheses because there is not much to tune in the linear regression model. Good. And finally, now we have, the linear regression model, but it is not smart yet. It is not trained yet on this data set, to understand and learn the correlations between the position levels and the salaries. So that's what we're going to do right now by using this fit method, which is exactly a training method that will train the model on these data. All right. So to do this, we're going to call our object first, linreg, from which we're going to call the fit method, which, remember, has to take as input the couple of matrix of features and dependent variable vector of the training set, right? That's what we did before, but remember here that we didn't split the data set into a training set and a test set because we want to leverage the maximum data in order to train our model, and therefore this time we're going to take the whole matrix of features x and the whole dependent variable vector y. All right, so here we just input x and y, and there we go, we built the linear regression model in a flashlight. So we're going to execute this. Here we go, and now we have not only our model but also a trained model on this data set. Okay, great. Now we're going to close this and we're going to focus on the heart of the matter, which is the polynomial regression model. I'm going to teach you now how to build the polynomial regression model. All right, so we're going to create a new code cell, and now we're going to go back to this slide to explain exactly what we're going to do. All right, so as you understand, what we've just built so far is this model. We only have one feature, the position levels, and the dependent variable vector to predict, which are the salaries. Now, what we're going to do is we're going to create a multiple linear regression model, but instead of having different features, x1, x2, and xn, well, these features will be x1, x1 squared, and x1 at the power of n. And we'll actually tune this parameter n a bit to try several powers. So not to confuse, the polynomial linear regression is not a linear model because you will see that it can learn some nonlinear correlations, but we call it polynomial linear regression because indeed there is this linear combination of the squared and, powered features, x1, x1 squared, and x1 at the power of n. All right? And so the process of building this model on Python will be first to create a matrix of the powered features, a matrix of features but not containing different features like x1, x2, and xn, but a matrix of features containing x1 as a first feature, then x1 squared as a second feature, and then x1 at the power of n as an nth feature. So that will be our matrix of features, and we will call it xpoly. And then we will create a linear regressor object, from the linear regression class, to integrate these powered features of this matrix of features in this new linear regressor. You see the idea? So it's a building process in two steps. We're going to first create the matrix of features containing these features at different powers, and then we'll integrate that into a linear regression model because indeed this is a linear combination of these powered features. All right, perfect. So let's do this. First step. The first step is to actually import this tool that will allow us to create this matrix of powered features, x1, x1 squared, and x1 at the power of n. And this class is called polynomial feature. So we're going to import it first, which we can get from, once again, of course, the scikit-learn library. There we go. But this time, we're going to get access to the preprocessing module, which contains that polynomial features class. This is a class because indeed, we're kind of preprocessing our x1 feature because we want to create out of x1, well, x1, x1 squared, and x1 at the power of n. So we're kind of doing preprocessing of the features. All right, so from this preprocessing module, we're going to import, well, that class, polynomial features. Perfect. I really like Google Colab. So polynomial features, And then, of course, well, anytime we import a class, the next step is to, of course, create an object of this class. And this object will be exactly the tool that will allow us to create this matrix of the features x1, x1 squared, x1 at the power of n. I will precise what n we choose then. We will choose several of them. But there you go. That's what we build with this polynomial features class. And so, well, we're going to call this object of this class poly_reg as polynomial regressor, but it's not exactly the regressor itself because, the final polynomial regressor will be the combination of this matrix of powered features and the linear regressor, and that's why we will call it actually linreg2, you will see. So polyreg will be created as an instance or an object of this polynomial features class. So we're going to paste that here, adding some parentheses, and that is where we're going to choose the n. That n here is exactly chosen in this new class. So first we're going to start with 2. Okay, we're going to build a polynomial regression model resulting from the equation y equals b0 plus b1 x1 plus b2 x1 squared, where x1 is of course the position levels and y is the salaries. All right, so let's create this. Let's precise degree, which is the name of the parameter for that n, equals 2, and then we'll try 3 and 4, okay? Then, next step. Well, the next step is now to proceed to this transformation of this simple matrix of features containing only x1, meaning exactly this column. So far, this is our matrix of features of only one feature. And now we're going to transform this matrix of a single feature into this new matrix of features containing x1 as a first feature, x1 squared as a second feature, and then that's it, because so far we started with n equal 2. But if we chose, for example, n equal 3, well, the matrix of features would be x1, x1 squared, and x1 at the power of 3. All right? So that's what we're going to do. And to do this, well, we're going to take, of course, our polyreg object again, from which we're going to call the method fitTransform again. You're starting to know this method. That's, the method that usually proceed to a transformation. And here, the transformation is to turn this matrix of a single feature into this new matrix of features composed of x1 as the first feature and x1 squared as the second feature. All right? fitTransform, then some parentheses. And then according to you now, what do we have to input here? Well, that's pretty obvious. That's exactly the matrix of features we want to transform into this matrix of squared features, let's say, right? So x of course, that's what we want to transform. X so far is only composed of this column. Okay, so fitTransform x, and now we have our new matrix of features. However, this exactly returns this new matrix of features, so now we're going to create a new variable which will be this new matrix of features itself, and we're going to call it x_poly equals what is returned by this fitTransform method applied to x. Great, so now we have exactly the matrix of features composed of the position levels and the squares of the position levels. Good. So now, according to you, what are we going to do? Well, as I said at the beginning, it's like now we have a new matrix of features, composed of these two variables here. And well, very simply, we just have to build a linear regression model that will integrate these features into this equation. Y equals b0 plus b1 x1 plus b2 x1 squared. Right? You see the idea? That's where the linear comes from. And therefore, well, you know what to do. You know how to create such a linear regressor, but we have to create a new one, which is of course different than this one, because this one is already trained on this matrix of single feature x, and therefore having already learned coefficient. So now we need to create a new one, which we're going to call, of course, linreg, and I'm adding _2, which therefore will be a new object of this linear regression class, adding some parentheses. And well, this object will be now trained on this new matrix of features composed of the position levels at different powers, and of course then the salary, because indeed we need the dependent variable vector to train the linear regression model and any machine learning model. All right, so the next step and final step is to, of course, call this new linear regressor object that we've just created, from which we're going to call the fit method, which will take as input, of course, this new matrix of features containing the position levels at different powers, and of course the same dependent variable vector, which are the salaries. All right, so let's do this. Let's input first x poly and then y, and there you go. you have your polynomial regression model. Congratulations! Now you know how to build a nonlinear regression model, and that's what we're going to see clearly with the next steps when visualizing the linear regression results first and the polynomial regression results. Now you know how to build such a model and you have them in the toolkit. So you're getting more power in machine learning, more knowledge, more skills. Congratulations! That's amazing. And now I can't wait to move on to the next tutorial to show you indeed the different results we get with linear regression and polynomial regression. So I'll see you in the next tutorial. Let's quickly run this cell in order to, get the model itself. And now whenever you're ready, let's proceed to the next tutorial for the visualizations. And until then, enjoy machine learning. Hello, my friends. So are you ready to visualize the linear regression results and the polynomial regression results to indeed understand that the polynomial regression model is way more adapted to nonlinear datasets, meaning to datasets with nonlinear relationships? All right, so let's do this. Let's create a new code cell. And now you actually know what to do. I should have told you in the previous tutorial to try to do it yourself first, because we're going to code exactly the same as, remember this piece of code we implemented to visualize the results of the simple linear regression model, but it's okay, let's do it together now quickly. So remember, the first thing that we have to do is call the matplotlib.pyplot module, which has a shortcut plt. Then from this module, we're going to call first the scatter function, which will allow to first, display on a 2D plot the different points of coordinates containing the real results, the real position levels going from 1 to 10 and the real salaries. So that's what we are plotting first, and then we'll plot the predictions. And so, well, here we have to input first the coordinates of these real points containing the real position levels and real salaries. And on the x-axis, we have, of course, the position levels. Therefore, the x-coordinates will be x, all the position levels contained in x. And then on the y-axis, we'll have the salaries, the real ones, and therefore the y-coordinates will be y. All right? And then remember, we need to add a color, and we'll choose, like last time, red. Perfect. So that's for the real results. And now we're going to plot the predictions. And to do that, well, we're going to call plt again, matplotlib.pyplot, from which we're going to call the plot method, because this time we're actually going to plot that regression line, in blue, like in simple linear regression. And then for polynomial regression, you will see that it's not a line, but it will be actually a curve. And still, we will use the plot function for that. So again, we have to enter the coordinates of the different points of this line. And for these coordinates, well, first, the x coordinates are still x, the position levels. But then the y coordinates will be, of course, the predicted salaries, instead of the real salaries. And to get them, well, we simply need to call our linreg object, not linreg2. Linreg2 is for the polynomial regression model. Linreg is for the linear regression model. And so linreg, from which we're going to call that predict method, applied, of course, to x, right? Containing the position levels of the matrix of features x. All right, and then we add a color. And like last time, we'll choose the color blue. All right, blue. And then we'll just improve or enhance our graph by adding a title, an X label, and a Y label, and finally display it. So you know how to do this. We call first plt, then the title function. So here we're going to add a funny title, like in quotes, of course, truth or bluff, right? This is the simple scenario I invented for this case study. And then we're going to precise that it's linear regression, the linear regression model. Okay, good. Good title. Now, an X label. So here again, plt.x label. And we'll choose, something simple like position level. Okay, perfect. Then a Y label. So I'm calling the Y label function. And we're going to enter salary, because on the y-axis are all the salaries, the real ones or the predicted ones. And finally, remember that we have to show the graph by using this show function. Perfect. And there we go. We're already ready to visualize the linear regression results. Are you ready? I'm going to close this so that we can see it very well. All right, let's make sure I didn't make any mistake. Yeah, it seems all good. So now let's press play, and here we go. This is the linear regression results. Let's scroll down a bit. All right, so first of all, to recap, The red points here are the real salaries, going from 0 to, I think, 1 million for the CEO. Yes, okay. So these are all the real salaries of this column, okay? And then the blue line is, of course, the regression line containing all our predictions, but the predictions of the linear regression model. So, first of all, we can see that, indeed, the linear regression model is not well adapted to this dataset. Because, indeed, remember that in simple linear regression, it was well adapted because each time, for each of the values of the features, well, the prediction was close to the real result. But here, for many position levels, for many values of the feature, well, the prediction is far from the real result. Here, for example, it is quite far from the real salary. Imagine if we wanted to use that model to predict if someone is saying the truth or bluffing about a salary that is contained here. Well, we would have offered a way higher salary than we would be supposed to. So that would not be the best negotiation. Okay, so that linear regression model is not well adapted. And same here, it is far from the prediction. Same here, far from the prediction. Here it's okay, but that's only for 2 points, 2 salaries. But then here it's super far from the prediction, and here as well. So clearly not well adapted, and that's why I wanted to show you this, because now you're going to see that the polynomial regression results are going to be much better. And now I'm going to show this to you right away. So I'm going to close this, and we're going to visualize the polynomial regression results efficiently by taking this code, because you're going to see that it's going to be almost the same. So I'm going to scroll down. I'll scroll back up to compare, create a new code cell, pasting that here. And now, according to you, what do we have to change here? Actually, something important. Please press pause on the video now and try to figure out, before I give you the solution, what you have to replace here in order to visualize the polynomial regression result. I really want you to think, because it's not that easy. It is easy, but it's not like what you would think at first sight. So please press pause on the video and make that change in order to make it work for polynomial regression results. All right, okay, so now I'm going to tell you the solution. Well, first, of course, we have to change our regressor here because we want to use our polynomial regression model, which is based on linreg 2. So that's the first change, linreg 2, yes. And now, in the predict method, do you think we need to keep x or change that by something else? Well, of course, we can't keep x, because remember, x is only that matrix of single feature containing the position levels. Remember that when we use the linreg2 regressor, which is the linear regressor, it has to be applied to the transformed matrix of features x into this matrix of features at the different powers. Position level, then squared position level, and then the other powers. Here we only chose n equals 2 so far, so we only have the squared position levels. But that's exactly what you need to change here. You can't keep x because it is the single feature, so you need to input here that transformed matrix of features x containing the different powers of that single feature position level. And that's, of course, exactly this polyreg fit transform method applied to this matrix of single feature x. So I'm copying this, and that's exactly what we have to input inside this predict method. You understand? So that was the little thing not to forget, and now you're all good. You're ready to have a beautiful visualization of the polynomial regression results. Let's just replace this linear here by polynomial, and now 100% ready. Let's visualize the polynomial regression results. And there you go. Now we have indeed a way more adapted regression curve coming indeed much closer to the real results, the real salaries. Indeed, if we compare to, I'm going to zoom out a bit so that we can see both of them at the same time. There we go. So if we compare these points where we had issues previously with the linear regression model, well, we can clearly see now that the issue is resolved, because indeed the predictions on this blue curve come way closer to the real salaries. And this is only with n equals 2. I'm going to show you then that with higher powers, n equals 3 or 4, well, we will get even better results. And I'm going to actually show this to you right away. So now what we're going to do is, well, we're going to keep this, but we're going to remove this, because we're going to retrain the polynomial regression model with a higher degree, let's take, for example, you can try with 3, but we're going to directly try with 4. So there you go. I'm going to remove the output, retrain the polynomial regression model on the whole dataset with therefore this time a degree of 4, which means that the polynomial regression equation will be salary equals B0 plus B1 times position level plus B2 times position level square plus B3 times position level at the power of 3 plus B4 times position level at the power of 4. So that will be the new polynomial regression equation. And so therefore, let's retrain it. Let's build this new polynomial regression model by just running this cell again. All right, so now we have it. And now, very simply, we're going to visualize the new polynomial regression results by clicking this cell here. And as you can see now, the polynomial regression model is perfectly fitting this data set. So here we clearly have overfitting, but that's okay only in this situation because we want to have a perfect prediction of the salary between position level 6 and 7. Okay, and now one final thing, because I really want you to have the best results and best visualizations. Indeed, as you can see here, what happened is that only some straight lines were plotted between each consecutive points of the dataset, right? And therefore that makes this curve not as smooth as we would hope for. So I actually prepared another code, but which we won't code together because this is just for the sake of having a more beautiful curve. So we're going to get it from the original implementation. It is actually right here. You see visualizing the polynomial regression result for higher resolution and smoother curve. So I'm going to take all this code and then paste it in our copy of the implementation right here in a new code cell. And you will see that we will get indeed a much smoother and more beautiful curve, as you can see, right? And the trick to plot this curve, I'm going to explain this quickly, is just to, instead of taking, the integers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, well, we increase the density of these points by taking not only these integers, but, 1, 1.1, 1.2, 1.3, 1.4, up to, 9.1, 9.2, 9.8, 9.9, 10. That's what this 0.1 means. That's what we call the step. All right, so you don't have to understand this. You can if you want, but this is something you will probably do only once in your life because I remind that usually your datasets will have many features, and here I only took one feature in order to show you the results on a graph. Because, if we had many features, I couldn't show this to you because we would have way too many dimensions. So don't worry too much about this, okay? But just appreciate the result, right? We have a very well trained and therefore very well fitted, but overfitted model for this data set. But that's fine because then, indeed, we will be able to get an amazing and accurate prediction to figure out if there is truth or bluff. So that's what we'll do in this next and last tutorial. We will first predict that salary of the position level 6.5 with linear regression and then with polynomial regression. I really encourage you to try to do it on your own first because it's actually not that difficult. The only new thing that you'll have to figure out will be to, figure out how to predict a single observation instead of a whole matrix of features of the test set. But really, if at least you try, you will definitely improve your Python skills. So, good luck, and I can't wait to see you in the next tutorial to find out about that prediction. And until then, enjoy machine learning. All right, here we go for that final step, predicting the salary of the position level 6.5 with both linear regression and polynomial regression. So we're going to start with linear regression first, therefore creating a new code cell here. And so now, I asked you to figure out how to predict a single observation, the dependent variable for a single observation, meaning the position level 6.5. Well, let's do it step by step. Of course, the first step you had to do here was to take your linear regressor object, from the simple linear regression model. And this object was named linreg, this one. And then, very simply, from this object, you're going to call the predict method to predict the salary of the position level 6.5. All right, so what exactly do you need to input here in this predict method to get such a predicted salary? Well, I'm sure some of you tried to directly input 6.5, but unfortunately this is not that simple because indeed you always have to input your observations in an array, right? That's what is specified here in the parameters. the input of the predict method should be an array-like or a sparse matrix. So an array-like is, for example, a numpy array or a simple array with double pair of square brackets. Well, I said it. That's exactly how you need to input an array, because generally in Python, an array is built with pairs of square brackets. If you add just a single pair of square brackets here, well, that actually creates a list, or you can also see it as a vector. But in order to create an array, well, an array contains several dimensions, like 2 dimensions in our case here, and therefore you need to add a double pair of square brackets. What does this double pair of square brackets mean? Well, the first pair of square brackets here corresponds to the first dimension, and the second pair of square brackets here corresponds to the second dimension. So the first dimension is actually corresponding to the rows in your array, and the second dimension is corresponding to your column. So for example, if I add, just to show you, if I add, for example, 5 here, that would create actually an array of 1 row and 2 columns. And if I add here a comma and then another pair of square brackets and then, for example, 2 and 3, well, this would create indeed an array of 2 rows and 2 columns. In the first row you would have 6.5 and 5, and in the second row you would have 2 and 3. So you see, the first square bracket here corresponds to the rows and the second one corresponds to the columns. All right, so let's go back to where we were, exactly this. So this indeed is exactly the format expected by this predict method, an array of 2 dimensions. Even if this only contains one cell, one value, well, it has to be in this format. And now, well, you're ready to get that prediction. So before we execute this, let's remember that this person asked for a 160K salary, and this is justified by the fact that this person earned a 160K salary in the previous company, which is what we have to check right now. And we're going to check that first with the linear regression model, which returns indeed a salary of $330,000 per year. So if we actually use this model to negotiate with that person, we would actually find it super weird, right? Because this predicted salary is way over the real salary that this person had in its previous company. So clearly, the prediction here is wrong, and that's what we can clearly see on the graph, the graph above showing the results of the linear regression model. 6.5 is somewhere around here, and indeed, if we want to get the prediction, we have to project it to that blue regression line, and then project it again to the vertical axis, which is around here, and indeed, that's what we get. This is multiplied by 10 to the power of 6, so indeed we get something around 330. All right, so anyway, that's a really bad prediction. So now we're going to get the good prediction, which we can clearly see here. That's 6.5, and we'll get a prediction around here, which will correspond indeed to the salary that this person mentioned. So let's do this. Let's create a new code cell here, and to get that prediction, we're going to do it efficiently. I'm going to copy this and paste here. And now, once again, I would like you to press pause on this video and figure out what we have to replace here to indeed get the predicted salary resulting of our polynomial regression model. So please press pause, and then I'll tell you the solution right away. Okay, let's do this. All right, so first, the obvious thing you had to change is, of course, the name of your regressor, because for polynomial regression, we named our regressor linreg2. And then, exactly the same thing as before, here we can't input that single position level, coming from the matrix of single feature, but instead, well, we have to exactly input, the features of this equation where x1 is equal to 6.5. And therefore, what we need to input as features is this array composed of the following features values: 6.5 for x1, then 6.5 squared for x1 squared, then 6.5 at the power of 3 and 6.5 at the power of 4, because now we have built a polynomial regression model with degree 4. All right, so here, the exact thing that we have to predict, and we can actually input that efficiently by, taking exactly what we input here in the predict method, that polyreg object from which we call the fit transform method, to transform this matrix of single feature x into this matrix composed of the several features at the different powers. And here, well, of course, the feature value that we will input inside this fit transform method will not be x, but not 6.5 directly, like before, but once again, a 2D array containing the value of 6.5, the cell of 6.5. And so that's exactly the same as before. We need to enter this 6.5 value inside an array. Just before we had x here, x is an array, and now we have to input 6.5 in a 2D array, just like that. And now there you go, we're ready to get our predicted salary resulting from the polynomial regression model. So let's find out right away what is that predicted salary. And wonderful, the predicted salary is $159,000, which is super close to the salary mentioned by this person, as the previous salary earned in the previous company. So now we can be 100% confident to hire this person because not only it is a good fit for the job, but also it is a very honest person. And we figured that out with polynomial regression. So congratulations, we all solved this case study. Not only we solved this case study, but you now know how to build a polynomial regression model and you added that in your toolkit. This is your first nonlinear regression model. Congratulations for that. Now we're going to build 3 other ones, starting with the SVR, support vector for regression, and that's what we'll do in the next section. Now, for those of you who also want to study R, well, you'll find that same implementation, but in R, of course, in the next section. And for those of you who only want to learn Python, well, join me in the section after that to first learn about SVR with Kirill and then implement the SVR model with me, which will be, by the way, on the same dataset with the same case study, so that we can actually compare the different results of our nonlinear regression models. So I can't wait to see you in these next sections, and until then, enjoy machine learning.
Hello and welcome to this R tutorial. So we already built 2 regression models. It was the simple linear regression and the multiple linear regression. And these 2 models were linear models. And now we are going to the next level because we will start to build nonlinear regression models. So that means that for data sets where there will not be a linear relationship between the independent variables and the dependent variable, these nonlinear regression models will be very useful. And speaking of problems with nonlinear relationships, this is the kind of problems that we will have to deal with in the future sections. So in the future sections, we will build nonlinear regression models to solve nonlinear problems. And today, in this tutorial, we will start with polynomial regression. So as usual, let's prepare the workspace by setting the right folder as working directory. So right now I'm going to my machine learning AZ folder, part 2 regression, then section polynomial regression, and here is the right folder. Make sure that you have the position salary CSV file, and you can click on this more button here, and then set as working directory. And now let's start with the usual first step of making a machine learning model. So this first step is of course the data preprocessing step. So to be efficient, I'm going to go to my data preprocessing template that we made in part 1. I'm going to select everything in that template, copy, and paste it in my polynomial regression model. This way. Okay, and now we just need to change a few things. So the first thing we need to change is the name of the dataset. So it's not data here. Data was the name of the dataset in the preprocessing part. But now in this regression part, the name of the dataset is position underscore salaries. So here we'll write position underscore salaries. And now let's select this line and execute to have a look at our dataset. Okay, and now let's see what will be our machine learning mission. So we are a human resource team working for a big company, and we are about to hire a new employee in this company. So this new employee seems to be great, a good fit for the job, and we are about to make an offer to this potential new employee. And now it's time to negotiate. Negotiate on what is going to be the future salary of this new employee in the company. And so at the beginning of the negotiation, this new employee is telling that he's had 20 plus years of experience and eventually earned 160K annual salary in its previous company. So this employee is asking for at least more than 160K. However, there is someone in the HR team that is kind of a control freak and always fantasized about being a detective, so suddenly decides to call the previous employer to check that info, that info about the previous 160K annual salary of this future potential new employee. But unfortunately, all the info that this person manages to get are these info here. This simple table of salaries for these 10 different positions in the previous company. So this HR member of the team runs a simple analysis on Excel or Google Sheets and actually observes that there is a nonlinear relationship between these position levels and their associated salaries. However, and moreover, this HR guy could get another very relevant info. This other relevant info is that this new employee that is about to be hired has been a region manager for 2 years now in the previous company, and that usually it takes on average 4 years to jump from being a region manager to a partner. So this new employee about to be hired was kind of halfway between level 6 and level 7, and therefore we can say he was level 6.5. So now this HR guy is getting all excited because he's telling to the team that he can build a bluffing detector using regression models to predict if this new employee is bluffing about its salary. So at the beginning the team finds it a little weird, but it's kind of curious to see what's going to happen. So here is the mission. This new employee that is about to be hired is telling that its annual salary was 160k in the previous company. Let's use polynomial regression to build a bluffing detector to predict if it's truth or bluff. Alright, and now that we get the problem, let's see if we need all the data set to train our machine learning model, which by the way is going to be the polynomial regression model. Remember, the machine is the polynomial regression model itself, and learning is related to the fact that this polynomial regression machine learning model will learn the correlations between the levels here and the salaries to predict any new salary of new levels that are not in this table here. For example, we want to predict the salary of level 6.5. Well, thanks to what our machine learning polynomial regression model learned on this info here, it will be able to predict the salary of level 6.5. Okay, so we notice that in this data set, this position column is strictly equivalent to this level column. You know, it's like we already encoded this position column, by transforming this variable into numerical variables, and therefore we will not include this position column in the data set where we will train our polynomial regression model, and we will only use these two columns, level and salary, so that the independent variable column will be this level column, and the dependent variable will be the salary column. So let's go back to our polynomial regression model, and here let's select these two columns we are only interested in. So to do this, we will reset the data set. So I'm taking my data set here, and again I'm taking my data set, then brackets, and in this brackets here we will input the indexes of the columns we want to keep to train our machine learning model. So let's see what these indexes are. Okay, so we have three columns. Indexes in R start at 1. So this column has index 1, this column has index 2, and this column has index 3. So since we want to keep these last two columns, then we want to keep the indexes 2 and 3. Okay, so let's input that. To input this, we can simply input to column 3. Let's check it out. Let's select this line and execute. And as you can see now, our data set, if we look at it, only has these two columns, level and salary. So as a reminder, level is the independent variable and salary is the dependent variable. So we will use the correlations between the levels and the salaries to train our nonlinear machine learning polynomial regression model to predict some new salaries, such as the salary associated to a 6.5 position level. Okay, so let's go back to the polynomial regression model. Our data set is well imported now, it's well prepared, we have everything we need, and now let's move on to the next step. So the next step is to split the data set into the training set and the test set, and actually this time, and only this time, we will not do that. And the reason is that we only have 10 observations here. So this is a very small data set. And by the way, I chose this data set because we're still shaping our intuition of machine learning. We're still learning the basics of machine learning. And therefore I choose this simple data set because we have 2 dimensions here. So we will be able to plot the form of the polynomial regression model itself, as well as the future nonlinear regression models. Okay, so let's go back to our model. And as I just said, we won't need to split the data set into the training set and the test set. So what I'm going to do now is I'm going to put all this section in comments. So let's do this. Press Command or Control plus Shift plus C, and that puts all your selected lines in comments. So no training set and no test set will be created. Okay, and the last step now is feature scaling. And the good news is that we won't need feature scaling either. And the reason is simple, it's that because a polynomial regression model is actually a multiple linear regression model with polynomial terms. You know, instead of having different features, like features that represent something very different, we are taking a first feature, which is actually the position levels from 1 to 10, and as the other independent variables that will be in our multiple linear regression model, we will take the squares and other exponents of these levels here. Okay, so actually that's done. That was actually very simple. No need for training set or test set, no need for feature scaling, just some little changes in the dataset here with the indexes, and we're all fine. We're ready to build our first nonlinear regression model, that is the polynomial regression model, and that's what we will be doing in the next tutorial. So I look forward to creating this bluffing detector with you, and until then, enjoy machine learning. Hello and welcome to this R tutorial. So in the previous tutorial we did the preprocessing phase, we imported the dataset and selected only the level column and the salary column. Then we didn't have to split the dataset into the training set and the test set because, as you can see, the dataset is a very small dataset with only 10 observations. And finally, we didn't have to apply feature scaling. So that made this first preprocessing step pretty easy. And now we are ready to move on to the next step, which is to fit our polynomial model to the dataset. However, I would like to show you how the polynomial regression model is a much more powerful model for our situation. And the best way to show you this is to actually compare it to a baseline model, like a reference base model, which will be our linear regression model. That's why in this tutorial we will build two models, the linear regression model and the polynomial regression model. And then we will compare the results, we will compare the graphic results and also the predictions. So you'll be convinced that the polynomial regression model is a much more appropriate model for this problem, and the main reason for that is that our problem is a nonlinear problem. Okay, so let's start by building this linear model. It's going to be very quick because we actually already did this. So we start by creating our regressor that this time we're not going to call regressor because we will build two regressors, the linear one and the polynomial one. So we will call it linreg. Here we go. And then later we will call our polynomial regressor polyreg. So linreg equals, and then remember we have to use the LM formula. And so we need to add some parentheses here. And then let's remind ourselves what we need to input by pressing F1 here to have a look at the arguments. Okay, so remember the first argument is formula. So the formula is very simply the salary, that is our independent variable, tilde. So I just pressed Alt N and then a dot here to take all the independent variables, but actually there is only one independent variable. So the dot here is strictly equivalent as just writing level. Okay, so perfect for the first argument. And then what is the second argument? It's data. So data, okay, so let's add this argument. Data equals, and now let's see. Okay, so in the linear regression section, we actually used the training set here as the data argument to train our linear regression model. But as we explained before, here we did not split the data set into the training set or the test set. So we are simply going to train our model on the whole data set itself, because it's a small data set anyway, and we want to have the most accurate prediction. So here simply we will just input data set. All right, and our linear regression model is ready. We are actually ready to build it. So let's just do it. Let's build our linear regression model. I'm pressing Command and Control plus Enter to execute. All right, linear regression made. We can have a quick look at the summary here. Summary linreg. So I'm typing this in the console and pressing Enter. And here are the statistical results of the model. We're doing this on R because, as you can see, it's really easy. On Python, we would have needed to import a class, create an object, but here it's really easy. So we can have a look. And we can see that the level has 2 stars here for the level of significance and is actually not a bad predictor of the salary. But wait for the polynomial model to see how it's going to be much better than linear regression. Okay, so now let's move on to the next level, that is the better model, polynomial regression, and let's build it. Okay, so as I mentioned, we're going to call this regressor poly_reg. All right, this way. And you know, since the polynomial regression model is actually a multiple linear regression model in which the independent variables are actually the polynomial features of one independent variables, as Carol explained in the intuition tutorial, well, we're going to use again the lm function as we did for linear regression. So here I'm just going to start by taking my lm function, add the parenthesis, and we're going to input our two arguments, formula equals salary tilde alt n, and then this dot here. But don't worry, we'll actually represent something else. So far I'm just putting the dot, and you'll understand what's going to happen next, which will make our polynomial regression build correctly. So then comma, and then we add our second argument, which is still going to be the data equals data set, because we're going to train our polynomial regression model on the whole data set. Okay, so now you must be telling yourself, wait, but this is exactly the same as linear regression. Well, that's true, and that's why we need to add a little something here to make this model a polynomial regression model. And this little something that we're going to add is actually the polynomial features. The polynomial features are actually some additional independent variables that are going to be the level squared, the level cubed, level to the fourth, level to the fifth, up to any degree you want. These are these additional independent variables that are going to compose our new matrix of features in some way, which will actually be the matrix on which we will apply a multiple linear regression model, which will make the whole model a polynomial regression model. So in short, a polynomial regression model is a multiple linear regression model that is composed of one independent variable and additional independent variables that are the polynomial terms of this first independent variable. Okay, so now that we get this idea, you'll perfectly understand what we're about to do right now when building our polynomial regression model, because what we're going to do is to build these polynomial terms. And to that extent, what we're simply going to do is to add specifically a new column here in this data set, which will be the level squared. So we're going to call this new independent variable level 2, and let's add this new column right now. So to add a column in a data frame, we need to take our data frame, so it's data set, here it is, and then we need to add a $sign here, and then we can add any name here, which will create a new column of this name and add it into our data set. So we're going to call this column level 2, because we're taking the level squared of our 10 levels. Then we add equals, and then we actually need to give the formula of the values in this level 2 column of our data set, and this formula is therefore the levels in our data set at the power of 2. So very simply, we're going to take all the levels of our data set by taking our data set and same adding this dollar here to take the level column, which is here. I just have to press enter. So by doing this, I'm taking the level column that is all the values of the level column in our data set. And now I'm going to take the square of all these levels in our data set. And so to do this, very simply, I just add hat and 2. That's it. That will just create a new column which will contain the squares of our 10 levels in our data set. So let's see. Right now my data set contains only 2 columns, level and salary. And if I execute this, here we go. Now let's have a look at the data set. As you can see, I now have 3 columns, level, salary, and level 2. And as you can notice, the values in the level 2 column are the squares of the values in the level column. Okay, and now we can build our polynomial regression model, because now this dot here not only contains the level column, but also the level 2 column. So this will build a multiple linear regression model where the independent variables are the original independent variable and the polynomial term of this first independent variable. And if you want to build a polynomial regression model with a higher degree, well, you would need to do the same here. You know, we can copy this line and paste it here and just add a level 3 column that will contain the cubes of the levels in the original independent variable level of our data set. And as you can see, it'll be very easy. I just need to execute this line, and this will add a level 3 column in our data set. And so now this little dot here will be the original independent variable level, the square values of our levels in level 2, and the cube values of our levels in the column level 3. You can add as many powers of levels as you want, but maybe we will stop here. We will see what is the best polynomial regression for our model, and so we will see what we'll get with this one. And now let's actually build the polynomial regression model. If we select this and execute, press Command and Control plus Enter to execute, and done, our polynomial regression model is created. Awesome. So we're gonna have a look. Let's type summary in the console, polyreg, and let's press enter and let's see what we get. Okay, so now what we can see is that these level 2 and level 3 polynomial terms that we created are actually statistical significant variables. But actually this table here does not show the real deal of the polynomial regression model for our problem. You will be much more convinced in the next tutorial where we'll be visualizing the graphic results, and you will perfectly understand why our polynomial regression, which is a nonlinear model, will make a much better job at predicting what we want compared to this linear regression model, because it's a linear model. So we'll check that in the next tutorial, and until then, enjoy machine learning. Hello and welcome to this R tutorial. So in the previous tutorials we made our first 2 steps of building our polynomial regression model, which were to preprocess the data, and actually that was really simple because we just needed to import the dataset and select the columns of interest. And then we fitted 2 models to our dataset, the linear regression model and the polynomial regression model. So we built the linear regression model as a reference of comparison of the polynomial regression model that we also built. And speaking of comparison, in this tutorial we are going to visualize the graphic results of these 2 models, and therefore we're going to make 2 plots here, 1 plot for each model where we're going to see the real observations and the predictions, and it's in this tutorial that you're going to be convinced of how more powerful the polynomial regression model is compared to the linear regression one. So right now, let's write the code to visualize those results. So we're going to do this with ggplot2. In case you didn't follow the linear regression tutorials on R, I'm just going to write the line to install the ggplot2 package. I'm not going to install it, but it's just in case you don't have it. And to check that, you need to go to the packages here and check if you have the ggplot2 package here. And so if you don't find it in this list here, you need to install it. And to install it, it's really simple. You just need to type here install.packages. You can press enter here. And then in quotes, you enter the name of the package, which is ggplot2. And then you just need to select this line and execute this line by pressing Command or Control plus Enter, and this will install the ggplot2 package without any issue. I'm not going to do it because mine is already installed, but you can trust me, it will work perfectly. So I'm going to put that as comment by pressing Command Shift plus C. All right, and now we can start to visualize the linear regression results. So as you can see in the packages here, the ggplot2 package is not selected here, so I'm going to need to select here. So either I can click here, or the better way is to automate the selection of this package thanks to the script. And to do this, we just need to add the line library and in parentheses the name of the package with no quotes, so just ggplot2 here, this way. And when this line will be executed, actually we can check it right now. As you can see, ggplot2 is not selected. I'm executing this line and now it's selected. Okay, so now that our ggplot2 library is selected, let's start building the plot. So we're going to do exactly like in simple linear regression. We're going to use the ggplot function, and then we're going to add the different components in the graph. So first we will add the real observation points thanks to the geomPoint function, and then we're going to add the predictions component thanks to the geomLine function. Then we're going to add a title to the plot thanks to ggtitle, and then a label to the x-axis with xlab, and a label to the y-axis with ylab. So very simple, exactly like before, we're going to make this graph step by step. Okay, so let's start with the first step. The first step is just to type here ggplot with parentheses, and that will initiate the plot. And now remember, we need to add a plus here, and that's where we start to add the different components. So the first component is the real observation points, and we are plotting them with the geomPoint function. So let's add here geomPoint, geom_point actually. Here it is, and now we input the arguments in the parentheses. Okay, so the first argument, remember, is the aesthetic function. So that's in this function that we will input the x coordinates of our observation points as well as the y coordinates. So let's do this. AES for aesthetic function. So in this aesthetic function, we need to input the x coordinates and the y coordinates of all our 10 observation points. So let's see what these coordinates are. Let's have a look at our data set. So our 10 observation points are characterized by their levels and their salaries. The x coordinates corresponds to the independent variable that is the level column here. And our y coordinates will be our 10 salaries here associated to these 10 levels here. So in short, the x coordinates are the independent variable values, that is the 10 levels here, and the y coordinates are the dependent variable values, that is the 10 salaries here. Okay, so let's input that. So x here is level and y is salary. However, since we did not specify that the data is data set here, our data set, we need to specify where we are taking the levels and the salaries. And to specify that, we need to add here dataset $, so that R understands that we are taking the levels of our dataset here. So it's going to be the same for Y. We're going to specify that we're taking the salaries of the column salary in our dataset. This way. Perfect. And now we can add another argument, because this aesthetic function was the first argument of this geom_point function. And remember, we can add a second argument, which we will add because we want to add a color to our points to then make the distinction between the real observation points and the predictions. And so we're going to pick the red color. So here I'm going to add the color argument and set it equal to red in quotes. All right, and now let's not forget to close the parenthesis of the geom_point function, because this parenthesis was for the aesthetic function. And now we are all fine. Great, and now let's add the second component, which are the predictions. So I'm going to add a plus here and add my second component here. So the second component is, as I just said, the predictions, and we're going to add these predictions component with the geom_line function. So exactly like we did in simple linear regression. So geom_line here, geom_line, and then parenthesis, of course. And again, we're going to take the aesthetic function combined to a color. So I'm just going to copy all this, right, and paste it in my geom_line function. All right, and now of course we will change a few things. So first, let's start with the simplest. Let's change the color. We're going to pick a blue color for our predictions. Here we go. And now what we need to change are the coordinates of our prediction points. So the x coordinates of our prediction points are still going to be the levels themselves, because we're just predicting the salaries of the 10 levels that we have in our dataset. So here we obviously need to take the only levels that we have in our dataset. So we keep here dataset $level. But then for the y coordinates, of course, something is going to change here, because by taking dataset $salary here, we're taking the real salaries of our 10 levels. That is the salaries that are in the salary column of our dataset here. So, of course, we need to remove this and replace it by something else. And what is this something else going to be? Well, of course, it's going to be the predictions of the salaries of the 10 levels according to the linear regression model. And to get these predictions, we're going to use, of course, the predict function. And so actually, that's exactly the same as in simple linear regression. In this predict function, we first need to specify the regressor. So the regressor is called linreg, because we're plotting the linear regression results, and our linear regression model was called linreg. That's our regressor, so linreg here. And now the second argument, remember, is new data. So new data here, and that's actually the data points we want to make predictions on. So very simply, that's our data set, because we want to get the predictions of the salaries of the 10 levels of our data set. So here we input indeed data set. There, perfect. So we're good, because we already inputted the blue color for our predictions. Great. And now let's complete this graph very quickly by adding a title, so plus here, and then we use the ggtitle function to add a title. Can you see how it's simple? It's starting to get really intuitive now. We were plotting the real observation points with the geom_point function. then the predictions with the geomline function, and now a title with the ggtitle function, well, everything will seem easier and easier for you. So for the title, we're going to add, as in Python, truth or bluff, just to give a funny name to our problem. And we're going to specify here that we are plotting the linear regression results. So we will just specify here linear regression. All right, so that's it for the title. And now let's add an X label and a Y label. So for the X label, we're going to add simply here xlab, parenthesis, then quotes, and then level, because our x-axis will contain the levels, and then plus ylab, parenthesis, quotes, and salary. And done! The linear regression results are ready to be plotted. So let's not wait anymore, and let's immediately have a look. So I'm going to select all this. I don't need to select this because ggplot2 is already imported. And now let's press Command or Control plus Enter to execute. And here are the linear regression results. So let's zoom on it and let's interpret. Great. Okay, so what is the first thing to understand here? Well, the most important thing to understand is definitely that we need to make the distinction between the real observation points, that are the red points here. Each point corresponds to one specific level and the real salary associated to this level on the y-axis here. And then we have our predictions on this line. That is that for each level, let's take, for example, the level 5. When we project this level 5 here on this straight line here, this point is actually our prediction point, and we can get the predicted salary by projecting this point here on the y-axis this way. And so we get a little less than $250,000. Okay, so that's the first thing to understand. The red points are the real observation points, and the points on this blue straight line are the prediction points. Okay, now the second important thing to understand is that our prediction result is actually a straight line. And the fact that it's a straight line is due to a particular reason. It's that the linear regression model is obviously a linear model. Each time you build a linear model in 2 dimensions, you'll get a straight line. And I'm highlighting this because the next model we're going to visualize the results is going to be the polynomial regression model, and this model turns out to be a nonlinear regression model, and you will see that it will not be a straight line anymore. And now let's give some interpretation. So first of all, we can see that this linear regression model represented by this blue straight line here is not fitting our data set very well, because as you can see, for some observation points, the prediction is actually pretty far from the real observation. That's the case for this point, and same for this point as well, and this point, and especially this point. Let's have a look at this point, for example. Well, this point is the real observation point. It corresponds to a 10 level and a $1 million salary. So it's definitely the salary of the CEO, and so that's the real salary. And now if we want to get the predicted salary for this particular observation point that represents the CEO, what we need to do is project this point on this blue straight line here, that is our linear regression model, to get actually the prediction point. And now to get the predicted salary of the CEO, we need to project again this prediction point onto the y-axis that contains all the salaries. And so we obtain that the predicted salary of the CEO is actually $620,000 according to our linear regression model. So imagine we're negotiating with a future employee that is about to be hired, and that was the CEO in its previous company. Imagine how furious this person will be if we tell this person that we believe it's bluffing because we think its salary is around $600,000, whereas its previous salary was in reality $1 million. The negotiation would probably turn really bad. So that's the first example of how this model can give poor results that can have a very negative impact on the situation, like the negotiation we are having right now. So let's see if the negotiation would actually turn bad for our real situation, that is this future employee that is about to be hired and that has a 6.5 level and that is negotiating its salary by saying that its previous salary in the previous company was 160K. Well, let's see. The 6.5 level corresponds to this level nearly. And when we project this level to our regression model, that is this blue straight line here, and if we project again this point on the salary axis, we get a predicted salary of well, it's more than $300,000 definitely, so actually we're way above what this employee said its previous salary was. So actually in this situation, in our real situation, the negotiation would turn well for us. But still, we want to get the accurate prediction, and clearly to do so we need to improve the model and make a nonlinear model which will fit much better the observation points here. That is, that we will make some kind of a curve that will approach much better all the red observation points here. So let's do this. Let's close the linear regression results and let's start to visualize the polynomial regression results. And you're going to see now how easy it is to go from the linear regression results to the polynomial regression results, because what we will simply do here is, select this and paste it here, and now you will see how we only need to change very few things. So as usual, let's start with the simplest. Let's replace linear here by polynomial. Okay, and now what do we need to change? Okay, so do we need to change something in the geom point function? No, of course, because we want to keep the same real observations, so that's okay. And then do we need to change something in the geom line function? Of course, yes, because here we are predicting the salaries of our 10 levels in our data set according to our linear regression model. So according to you, what do we need to change here? Very simply, well, actually we just need to change the regressor in the predict function, and instead of taking the linreg, which is the linear regressor, we're going to take the polynomial regressor that we called polyreg. And that's it. That's actually all we need to do to visualize the polynomial regression results. And you'll see that in the next sections, it will actually be the same. We will only need to change the regressor to plot the new graphic results of our future regressors. So that's very nice. We're actually ready right now to visualize the polynomial results. So let's do this without waiting. I'm going to select this and press Command and Control plus Enter to execute. And here it is. As you can see, this is not a straight line anymore. Let's zoom on the graph. All right, so as I just mentioned, the first reflex to have as a machine learning scientist is that this is not a linear model anymore. And by the way, congratulations, you just made your very first nonlinear model. We're going to see plenty of other nonlinear models in this course, but this is your first one, so congratulations. So, as you can see, it's not a straight line, now it's a curve, and we can immediately see that the curve is approaching much better all the red observation points. And especially for the CEO here. The CEO wouldn't get mad now if we negotiated with him its future salary in a new company, because now the prediction is much closer to the real observation point. And let's check our employee that is about to be hired and that has a 6.5 level, while 6.5 is around here. And when we project 6.5 on our polynomial regression model represented by this blue curve here, we get a predicted salary. Here I'm projecting the point on the curve back again on the salary axis, and we get actually a salary that is coming much closer to the salary mentioned by this future employee, which is around 160K here. Well, we don't get the accurate prediction yet because that's what we're going to do in the next tutorial, but definitely this model is fitting much better the dataset. And now, just for fun, let's add a new degree to see how this model can still be much improved and almost passing by all the points very accurately as we add more degrees. So let's check it out. Let's close this and let's add a new degree. So very simply, what we're going to do is add a new degree here by copying this line, paste it here, and we're going to add a new column in our data set, level 4, that will correspond to our original independent variable level at the power of 4. And so therefore here we need to compute it this way by taking the 4th power of level there. And now let's execute this line to add the level 4 column in our data set. Now you can check to see that it's here, level 4, perfect. And now let's reselect this to rebuild our new polynomial regression model with this 4th degree now. So executing, new polynomial regression model created, and now let's have a look at the results. So these are the previous results corresponding to a polynomial regression model with a 3rd degree, and now let's look at what happens with a 4th degree. So I'm going to select this and execute, and here are the polynomial regression results for a polynomial regression model with a 4th degree. Okay, so as you can see, we can zoom on it if you want. As you can see, the line is actually strictly passing by all the red observation points, and now the CEO would be even happier with the negotiation, or should I say even less furious, because the prediction now is actually almost the same as the real observation point. That is, the predicted salary is almost the same as the real salary. Okay, and same for our 6.5 level employee. When we project this 6.5 level here on the curve and then project it again on the y-axis, that is the salary axis, we get a value around what he said, that is 160K. And for those of you who are interested in having a more continuous curve here like we did in Python, I will add the code for that job in the R file provided in this section. You can check it out for fun, and this is the model we're going to use to get the accurate prediction of the previous salary of this new employee that is about to be hired, and we will compare it to the salary that he pretended to have in its previous company, and eventually tell our final verdict whether it's truth or bluff. So I look forward to doing that with you in the next tutorial, and until then, enjoy machine learning! Hello and welcome to this R tutorial. So in the previous tutorials we did the exciting step. We created our two regressors, the linear regressor and the polynomial regressor, and we visualized their results. So if we look at our graphs here, well, if we take the first one that we plotted, that is the linear regression graph, we obtain this straight line here that, besides its name, indicates that it's a linear model, and we saw that this model doesn't fit to the data very well because, as you can see, most of the prediction points are far from the real observation points. And then we were more satisfied when we visualized the polynomial regression results, first with a 3rd degree, so that's the polynomial regression model with a 3 degree, and it's actually much better. We can see that the model is fitting much better to the data set, since obviously the predictions are getting much closer to the real values than the previous predictions with the linear regression model. So that was much better, and then we did even better by adding a new degree to our polynomial regression model, and we actually obtained this model that we have here. And now we can clearly see that this model is fitting very well the data set, because all the predictions are very, very close to the real values, and for some of them it's actually the same. So that's definitely an excellent model for us because we are trying to make the most accurate prediction as possible. We are trying to predict the previous salary of a potential future employee that is about to be hired, and this predicted salary is at the heart of the negotiation because this employee is telling that its previous salary was 160K and is asking for more than that. And therefore, we are trying to predict if this 160K salary is the truth or a bluff. Okay, so now that we get this curve and now that we see that we have an excellent model for our problem, we are going to validate this model, and this is the model we are going to choose to make our final accurate prediction. And that is what we are going to do in this tutorial. So let's do it. I'm actually going to this new code section that I prepared for you. So a first one to predict the salary associated to a 6.5 level according to a linear regression model, and then the second code section will predict the salary of the 6.5 level according to our polynomial regression, this one right here with a 4th degree. Okay, so let's start with the linear regression prediction. So we're going to do exactly the same as in simple linear regression. We're going to use the predict function, but actually something that's going to be different and will interest many of you. This time we're not going to make some predictions on a whole test set, that is on a vector of observations. We're going to make a single prediction. That is, we're going to make a prediction of a single level, which is going to be the 6.5 level. So you're going to see that the syntax is going to change, the technique to make this prediction is going to change, but it's actually as easy. So let's do it. We're going to call this prediction ypred as before. So be careful, ypred was before a vector, and now it's only going to be a single prediction value. So let's still call it ypred anyway. And same as before, we're going to take the predict function. So let's here take predict. Here we go. And now in this predict function, remember we need to specify first the regressor we want to make the predictions with. So that's the first argument. And then the second argument is the new data of which we want to make the predictions. Okay, so let's input the first argument. The first argument is our regressor. And since we're predicting the result with the linear regression regressor. And since we called this regressor linreg, then the first argument we need to input here is linreg. All right, so that's our regressor. And now we need to input the new data of which we want to make the prediction. So this new data is, as you understood, a single element, a single observation point. And this observation point is actually the 6.5 level here. So what we'll do now is to actually, since this 6.5 level doesn't exist in our data set, we actually need to create a new data frame containing this 6.5 value. We're not going to add this 6.5 level in our data set. We're going to create a new data set of only one line and only one column, that is of only one cell actually, and this cell will contain the 6.5 level. So let's do this. The syntax in R to do that is very simple. We just need to type here data frame separated by a dot. So frame, here we go, data frame. And now, as you can see, it automatically added some parentheses. And in these parentheses, we need to input level equals 6.5. And that's it. That's actually all you need to do to make a single prediction using the predict function with a specific regressor that is here, the linear regressor. Let's check it out. Let's select this line and execute. Okay, ypred correctly generated. So as you can see, ypred is in the values here. We can already see the predicted value of the 6.5 level salary, and it's actually $330,000. So much higher than what this employee mentioned its salary was. So that's actually a good start for us. But remember, we don't want to keep the linear regression model. We want to keep the most accurate regression model. That is, of course, the polynomial regression model. So what we're going to do now is make the same prediction, but this time according to our polynomial regression model. So let's do this. Let's be efficient and copy this line because we will only need to change a few things, but you're going to see that this time it's not going to be that simple as here. It's going to be simple, but not that simple. We just need to add several arguments. And why is that? The reason is very logic. It's because since our polynomial regression model learned the correlations on this data set containing the level column and also the level 2, level 3, and level 4 columns, well, when we create this new data frame containing only the 6.5 level observation, well, since our polynomial regressor is based upon these 4 columns here, level, level 2, level 3, and level 4, then that means that in this new observation cell that we created for our level 6.5, we not only need to input the level, but also the level 2, the level 3, and the level 4. And that's what's going to change here. That's the only thing that is a little less simple than what we did before, but that's still very simple because as you can see, it will be very quick and easy to add these values. So let's do this. Let's not forget to change, of course, the regressor here. It's not linreg anymore, it's polyreg, because polyreg is the name we gave to our polynomial regression regressor in this formula right here. Okay, and so now, as I just explained, we just need to add here the polynomial features of our levels. So that means that we need to add level 2 right here. And don't worry, we don't need to compute it ourselves. We just need to add here 6.5 squared. And that will do it because, level 2 contains the square values of the values in the level column. And that's why here we add level 2 equals 6.5 squared. And same for the other levels. We actually made a 4th degree polynomial regression model. So we need to add here 4 levels. And so I'm adding here level 3 equals 6.5 at the power of 3. And our last level, level 4, equals 6.5 at the power of 4. And that's it. It was only this little less simple thing to do, but now it's ready. So let's check it out. And actually we're about to find out the final verdict of the heart of the negotiation, which is the most accurate predicted salary that this future potential employee had in its previous company. So let's find out. I'm going to select all this and press Command and Control plus Enter to execute. Here we go. So what is the final value? It's $158,000. So very close to what the employee said. He said 160K and we predicted 158K. So that's awesome news because not only we can proceed to the right direction of our negotiation, but also we can now be relieved that this new future potential employee is very honest, and that's one of the best qualities to have in life, including professional life. So, verdict, is it truth or bluff? Well, the final verdict is truth. So we're ending this tutorial as well as this section about polynomial regression on a good note. So happy ending. Not only the verdict is truth, but also you can be proud of having built your very first nonlinear regression model. So congratulations again. And you're going to see that in the next sections we will be introduced to some new nonlinear regression models, and some of them are fascinating. So you'll see. I look forward to seeing you in the next section. I'll just add a final tutorial here, but that's not to build any more models. It's just that we're going to make a regression template, to build a lot more efficiently the next regression models. You'll have, of course, the code template, and you'll see how it will be very useful. So I look forward to seeing you in the next section. Congratulations again, and until then, enjoy machine learning. Hello and welcome to this R tutorial. So in this tutorial, we're not going to make any machine learning model. We're just going to make a template, and this will be our regression template. So it's a template that is going to be very useful for the next nonlinear regression models we're going to make, like the SVR model, the decision tree regression model, and the random forest regression model. So we're going to use this template to build these three next models on R, and also you can use this template to create a regression model for your specific problem, because as you can see, you will only have a few things to change so that you will build your machine learning model very efficiently. So let's make this template, and to make it, we're going to go from what we did in polynomial regression and generalize the whole thing. So I'm going to take everything from here up to the end, copy, and I'm going to paste that in the template. And now let's make this template. Okay, so first of all, let's start with the beginning. So the beginning was about preprocessing the data. So actually there is nothing to change here. We will keep, of course, these two lines because we will work on the position salary CSV file and build our nonlinear regression models on it. And for the same reason as before, we won't need to split the dataset into a training set and a test set because this is a small dataset. And we will leave feature scaling as comments here, since most of the libraries don't require us to apply feature scaling manually. So all good for the preprocessing phase, and this will be the first part of our regression template. Great, now let's move on to the next part. So the next part is about creating the model. Creating the model and fitting it to the dataset. So first of all, in the previous tutorial, we built two regression models, the linear regression model and the polynomial regression model, and that was just to compare the two results and to show you that the polynomial regression model was much more appropriate to our problem because it was a nonlinear regression model as opposed to the linear regression model, which is a linear model. So we only did that so that you can understand very clearly the distinction between linear models and nonlinear models. But now that it's getting pretty clear in our mind, we are going to get rid of this section here about linear regression, because now we get the idea. And we will only focus on the new nonlinear regression models themselves without comparing them to the linear regression model. But keep the graphic results of the linear regression model in mind. Keep in mind that it was a straight line, not fitting very well the data set, and therefore was not much appropriate to our data set where the data is non-linearly distributed. Okay, so we're going to get rid of this. Done. Now we only have this code section here that creates the nonlinear regression model itself. So we're going to get rid of this because this corresponds to the polynomial regression, and to generalize we will just add a comment here to specify that this is where we have to create our regressor right here. Okay, and here we can also replace polynomial regression by the regression model, and we are all good with this section. Okay, now let's move on to the next one. The next one is about visualizing the results. So for the same reason as what we did in this section to fit the regression model to the dataset, we will get rid of the graphic results of the linear regression model because we have them in mind and we only want to focus on our future nonlinear regression models. So let's get rid of this, and now we only have the graphic results of our future nonlinear regression model. Okay, and the great thing about this template is that in this section we won't need to change anything, well, almost anything, because we're going to replace polynomial regression by regression model, and we're going to change this polyreg regressor here by regressor, because before we called it polyreg because we also had our linear regressor linreg, and so we needed to make the distinction. But now, since we got rid of the linear regression model, we will call our future nonlinear regression model regressor here, and that's why we input regressor here in the predict function. So basically, when we get to this section, when we build our future nonlinear regression model, the only thing that we will need to change is actually the title here. Basically, we don't have anything to change here, and that's the great thing about this template. However, of course, if you're using this template on your dataset and your problem, well, the only thing that you will need to change are the names here of the independent variable and also the name of the dependent variable here. That is, you'll have to replace salary by the name of your dependent variable. But that's all. Okay, and we're finally getting to the last section of this code template, which is about predicting the final result to get our final verdict. Okay, so same reason as before, we're going to get rid of the linear regression part for this. So here we go, goodbye. And now we are only left with the polynomial regression prediction. Okay, great. And so now we just need to change something here. Well, first it's the name of the regressor, because before the name of our polynomial regression regressor was called polyreg. And now, since we won't make the distinction between a linear regression model and our nonlinear regression model, well, our regressor will be called regressor. So here, regressor. And here, for polynomial regression, we needed to input the polynomial features of our data frame that we created in our data frame. Well, we won't need to do this for the next nonlinear models, because this is strictly specific to the polynomial regression model, where we need to add those polynomial features. And so we will get rid of this and we'll get something very simple. It's actually this line that will perfectly predict the salary of this 6.5 position level. Because in our future nonlinear regression models, there won't be those polynomial features in the dataset, so we will only need the original independent variable here, and especially this 6.5 value of this independent variable. So that's why we have everything we need with this simple line. Okay, great. And now the last thing that I'm going to do is maybe to take this code section here, cut, and I'm actually going to place it between the creation of the model and the visualization, because I like to keep the best for the end. And for me, the best part, the most exciting part, is the part where we visualize our results. And for a second reason is that we know that our problem is a nonlinear problem, and that therefore we need a nonlinear regressor. And we're definitely already convinced of that. So that's why we don't need to execute this code section before this one to convince ourselves that we need indeed a nonlinear regression model. So therefore, for the next regression models, we will make the prediction before visualizing the results, and that's why I'm putting that here first. Okay, so I think the template is ready now. Well, maybe we need to change the polynomial here to generalize the template as much as possible. So we'll replace polynomial here by, well, actually, let's just put predicting a new result. All right, and here we can replace polynomial regression by regression model. All right. And now, just to finish this template, for those of you who are also interested in getting a smoother curve in your regression model results, well, there is this trick we can do to increase the resolution, and we're going to do that right now. So it's just an optional code section that I'm adding here in this template. I'm going to copy this because we will have just a few things to change. And for those of you who really want a very smooth curve when you visualize your regression model results, well, you can use the following code. So the trick is to actually create a new sequence of levels. That means that here, when we are predicting only 10 salaries of the 10 levels, well, what we're going to do now in this section is that instead of predicting only 10 salaries of 10 levels, we're going to predict a lot more than 10 levels. And to do that, we will build a vector of imaginary levels that will actually be levels from 1 to 10, incremented by 0.1. So that means that we'll consider level 1, level 1.1, 1.2, 1.3, up to 9.6, 9.7, 9.8, and 9.9. So that's what we will create in this sequence, and therefore here, instead of predicting only 10 salaries, we will predict actually 90 salaries of 90 levels. So that's the trick, and to build this sequence, it's actually very simple. We're going to call this sequence XGrid. because XGrid will replace dataset $level here and dataset here. And this XGrid is going to be defined as sec, which is a function that builds a sequence. And so in this function, we need to input 3 parameters, the lower bound of your sequence. So that's actually min dataset level, because by doing this, we're taking the minimum of all the levels in your original dataset. All right. Then the next parameter is the upper bound of your levels. That is level 10. And therefore, we do the same with the max here, max dataset $level. All right. And the third parameter is the step. So that's where we increase the resolution and make our fitting curve smoother, because here we're going to take a step of 0.1. And therefore 90 levels will be created here from 1 to 10 incremented by 0.1. All right, so that's actually done. And now we need to replace dataset $level here that originally took the 10 levels of our dataset. So we are replacing that by XGrid. And same here, we need to replace dataset here by a new data frame, because this new data argument here is expecting a data frame here. So we cannot replace it directly by XGrid here, because XGrid is not a data frame, it's a sequence. That is, it's a vector. So what we need to do here is use this little trick again, but don't worry, it's quite simple. We need to use this data frame, data.frame command here that will actually create a data frame. And in parentheses, we're going to specify that we want to create a data frame of new levels. So I'm taking the variable level here, and then equals, and that's where you put XGrid. Because by doing this, data frame level equals XGrid, we're just creating a new column of levels containing all the levels in this sequence XGrid here of levels. And that's it. This new code section is ready to plot your regression model results in high resolution. And actually, we're going to specify here that it's for high resolution and smoother curve. All right, and that's actually ready. So you can try it on either, your polynomial regression model that we made in this section, or you can use it on the future nonlinear regression models that we're about to build, and you will see the difference between these two. But then if you want a more simple code, you can use this one. Or if you have, for example, a data set with 100 observations incremented by 1, then this is the code you need to execute, because then you wouldn't need a 0.1 step to build your different points of your fitting curve. All right, so now the template is ready. We're actually ready to use it for the next nonlinear regression models that we're about to build. We will do that in the next sections, and you're going to see how we will be so efficient at building them. So I look forward to creating these models with you. It's going to be very fun, and we will make them in the most efficient way. Enjoy machine learning!